Okay, so so thanks for inviting me, and today I will be like giving like a very introductory crystal tutorial, basically on how to set up the input parameter files, and basically how to run the crystal program. And this is I think this tutorial is designed for basically mainly for like the next generation of group members, and for those of you who never used crystal before. So so I will have a okay. So I will have an outline showing here. Will be covered in this very brief tutorial. So first, I will introduce how the ICSD data, like basically how to search for like necessary crystal structure information in the ICSD database, and then basically how to set up different crystal input script, including like the introduction for Gaussian basis set format, and how to use pseudopotential inside crystal, and how to prepare a anti-ferromagnetic calculation in crystal. And also at the end, the crystal package contains two different programs. One is called crystal, and the other is called properties. So we will use the property program, so separate from crystal program, to compute those different one electron properties, which includes the band structure calculation. So that's the outline. The first thing we are going to introduce here is how to obtain the crystal structure information. So personally, I use the inorganic crystal structure database, the ICSD. Yeah. So on the slide, I am showing a ICSD page with UMich login. So this is the page you will see after you use the list basically put on the left of the slide, and after you log in, you will see this page. So on this page, so there is a panel on the lower left of the page. It contains a list of advanced search options. So for us, chemistry is the most frequently used one. And if we click on click on each option listed here, the content of the center section is also going to change based on the option you choose. So now, if we click on chemistry, you will be taken to this page. So you will have to fill in certain information to this empty form. The first thing is the composition. So you will type in just the elements of the system you're interested in. And so for instance, I am interested in I am searching for the crystal structure of diamond, say. We know the diamond only contains carbon, so I input C in the composition, and number of elements is equal to set to 1. And then what else? Then to narrow down the search result, I enter the diamond as the mineral name below, so that I will not be seeing the result for graphite, for instance. And if I am, for example, searching for iron oxide, then I will be enter Fe and space O for composition, and the number of elements set to 2. And in the structure formula, I will enter Fe2 space O3. And we obviously do not need to fill in like all the information in this middle panel in this form. We just provide a selective like the data we need can be like quickly and basically accurately found. So after entering the necessary information on the central panel, we click on the Run Query button on the top right over here. Okay, so that should be it. Okay, so this will take us to the page with the list of search results. Normally, this list is going to be very long with hundreds of results. So in this case, we will want to narrow down the options that are available by basically use either the most recent, basically by looking at most recent result or only the high quality data. So the first thing I is to filter out only the high quality data. So if we click on the like the bottom box in red, we will be basically you will see a pop-up window with like different options. We will click on the quality filter and select high quality data only. This will basically refresh the result list for only displaying high quality data, and if we so basically the result you will see after this filtration is something like what I display on the page. So just to mention that I am only like showing or to mention I am showing the result different from like diamond in this case, because I want to show you what is boxed in the lower in the bottom of the page. Basically, you can see we have like 50 different results, search results, and this is really like when we want to narrow down the sections. So the star symbol, also boxed in red, represents like the high quality data. So after the filtration, only those data with stars are going to be displayed on the page. So another way of selecting high quality data is by clicking on the star in the top bar. So you can easily like select and then like unselect high quality data. Yeah. And to look for the most recent data, you can click on the publication year to the list. Basically, so you will see the result in the ascending or descending order in terms of like year it's published. And also, we probably want to also pay attention to the temperature column, because the lattice constant may differ a lot based on like the temperature. So this is something also you have to pay attention to. So now I'll try to order the search result based on the year it's published. And apparently for this example case, we're lucky. So the most recent result is a certified high quality data. So, and by checking the structure type, we see it says sodium chloride. And this is telling you that the nickel oxide has the structure type as rock salt. So, which I personally know for the type of structure I'm looking for. I'm looking for like nickel oxide in a rock salt structure. And in case of diamond, you will see the keyword diamond printed in this column. So the ICSD are also having like showing this HNM, the Hermann-Molgren notation, and this contains the information for the space group of the crystal structure. Okay. So after clicking on the select result, so basically the top one, you will be taken to a page that contains the very detailed information for the corresponding crystal structure. You will see the cell parameter A, B, and C for the length. So in this case is 4.17, and alpha beta gamma for the angle. We know rock salt has like cubic structure, so A equals B equals C in this case, and all the angles are 90 degrees for sure. And this is the necessary information for a crystal calculation. So we want to copy and paste that. And in the green box, you will see this base group number 225 for nickel oxide. This is also the information you will need in the crystal input file. So also want to copy that. And if you want to double check if the data are reliable provided here, the information boxed in blue are the titles and DOI of the related literature.
Yanbing, we lost you.
Drop down option. Okay.
Could you repeat the last sentence?
Okay.
We lost you. The last we had was DOI.
Okay. Let me try to go back and disable my video. How are you? Can you hear me now better?
Yes, but we just lost you only for a second. So the last. So the last thing we heard was that you listed the DOI of the relevant literature, and then there was like a break for a sentence we didn't hear.
Okay. I'm just saying, like, just to check if anyone is interested in like how this like lattice parameters and everything geometry was obtained, and experimentally they could check the literature and check if they think the data are reliable enough to be used. So then I was trying to say for this, or the orange box, you will find the geometry for the crystal structure, which is also necessary for crystal calculation. And so basically, if you click on like the drop down, like the option, you will, so for example, if you click on the published crystal structure data, you will be taken to this page. So, so in this section, you will see the system to basically, we know we are looking for a cubic system, which is correct, and space group again, and the which might be necessary if you are like searching for some additional information of the crystal structure, and for a the geometry that is boxed in blue in this table. This is the information you also want to copy and paste into the crystal input file. So for example, for nickel oxide, we have like one nickel and one oxygen in the unit cell. And this table is giving you the scaled three-dimensional coordinates for each corresponding atom, so X, Y, Z. And this is also the information, basically, this is exactly the information you want to input into the crystal input file. So the other website I want to share, so apart from the ICSD database, I personally also using the website showing here for cross-check and obtaining some additional information. So on this website, you can search for the specific crystal lattice information by searching, say, space group, Pearson symbols, and all the other like things listed here. I personally always use the space group number for search, just because numbers are easier to deal with. And it's just personal taste. So if we click on the space group, oh, before that, so this page might be looks familiar to some of you who had run like any like periodic calculation before, because this is like a site that's been commonly used. So this is actually the older version of the website I was showing over here. So, but this website has already like, so they stopped maintaining this website. So for any of you who are actually using this, you might want to actually go to the newer version. So if we click on the space group option, you basically will be taken to the page showing on the left. So this page is the geometry. Basically, it's basically having telling you the group your crystal structure actually falls in. So they're basically listing everything here. So for example, for triclinic groups, the space group number is between like 1 to 2, and for monoclinic, the space group number is between like 3 to 15. So like in the ICSD search result, we know that the nickel oxide falls into the cubic space group with a space group number 225. So basically, we will be looking here. So we know cubic space group has number from 195 to 230. So 225 falls between these two numbers. And then if we click on here, we will be taken to a page on the right. For space group 225, if I basically search 225 on the website, because it's a very long list. And then even under 225, you will basically see a long list of different crystal structures like falls under this category. And basically, you have to basically read the labels and trying to find the corresponding one, structure that you're looking at, which has like the same structure as sodium chloride. So we click on that, and okay, so that page, they're like, of course, a list of very useful information, but I was only showing some selected information here. So what I normally first, I would check the information box in red are indeed corresponding to the information we found on ICSD, and just to cross-check and make sure we are not looking at the wrong structure. And I sometimes find it the information box in orange here are to be useful, as it tells you like what are some of the other compounds that shares the same structure type as compound you are searching for. And you will see basically here you can see that the nickel oxide is actually listed here, yeah, and also so as magnesium oxide and lithium fluoride, and for example silver chloride. These are all like the similar other structures I've been like running before. So the information, something we've seen before, that is the unit cell geometry. So as you can see, the first atom has the coordinate 0, 0, 0, and the second atom has like 0.5, 0.5, 0.5, which are like identical as showing in the ICSD. The information box in green is actually the extra things that not necessarily useful for crystal program though. So because this information was like somehow embedded already inside the crystal program for most of the common crystal structure type. So by inputting this group number, crystal program will automatically search for this information. But for like, for example, other calculation like pi-SEF, sometimes you just have to input the unit cell like translation vectors manually. So you can use this information to construct them basically if necessary. Okay, so so you might be like wondering how, okay, so now we have everything we need to construct basically a crystal input file. So now I'm showing an example over here. So to run a crystal calculation on Poly, you will basically first need the crystal. I was basically putting this path over here. This is the path that I am using. I'm not 100% sure if this path is still available because obviously like things can change. So so this is actually in like Emmanuel's directory. So this so look for this crystal executable. This is the executable that you'll be using to submit the job basically. And we will specify two file names. One is called diamond dot with extension D12. So diamond is of course like something you can name it randomly as long as like it provides enough information. It tells you what is contained in the file. But D12 is the extension that you'll be using for a crystal calculation. So with like using this crystal executable, and you're directing all the output of this calculation to a file. I name it diamond. You can name it something else. Dot out. So this is the output file. So inside this diamond dot D12 D12. This is basically the script specifically for crystal. So in this tutorial, I will be going through the script line by line, and for by like so if you are interested for like more extensive like details, you should always like search for the user manual provided by Crystal. So Crystal 17 manual. Usually the first option, which is the PDF file, is actually the user manual. So you can download it and or read it like online. That's up to you. So back to the input file. The first line is a descriptive line. So just for the users, for yourself, and probably for like future people, like researchers who actually are going to reuse your input file. So it's for them to understand what this input file is about. So the Crystal program will not try the first line. So I could see which is the element name and diamond, which is structure name. So just for my own reference. And on the second line, I put crystal capitalized. And this is actually a keyword. And this is telling the program that we are running a three-dimensional calculation. So you will be putting SLAB, like SLAB, for two-dimensional system, and polymer or helix, for like one-dimensional system. So again, like the details can be found in chapter 2 of the user manual. And going to line 3, the first 0 over here is telling the program that we are going to input space group number for the program to identify the crystal structure, which I actually did. So on line 4, I entered 227 for diamond, which is space group number for diamond. And the second 0 in line 3 is telling the program if the cell are hexagonal, like are hexagonal type or like rhombohedral type. So for hexagonal, you only input the lattice constant A, B, and C. And since for diamond, we have A equals B equals C. So in line 5 here, I was putting 3.567 as the lattice constant. And that's it. I don't have to repeatedly like input same value. You only have to input 1 if they are all equals. The third 0 in line 3 is setting the origin of the reference frame. And say line 2 to line 6 about like the general like the cell crystal structure setup can be found in chapter 2 of the user manual, right below like the information for this crystal keywords. And going to line 6, you have to input the number of atoms in the asymmetric unit cell, like the reduced like unit cell. And line 7, you are basically entering the corresponding information. So in 6, we say we only have like 1 atom. So here in line 7, we are inputting the information for that specific atom. So clearly, the first 6 is the atomic number for the 0.125, 0.125, 0.125 is the XYZ coordinates for the like the geometry for that atom. And this is the information that you basically get from this ICSD database under the geometry section. And now for line 8, we put a keyword basis set, telling the program to find the basis set for the calculation, basically the line below the keywords. And here I was showing a specific example of putting the basis set in a separate file. So instead of just copy and paste the basis set, you find that line under the keyword, I actually did use a separate file. So just to make this input file like clean. So it is supposed, this separate file is supposed to be named basisset.dat over here.
Yanbing, if you can still hear us, your voice cut out.
Yes, I can hear you. Can you hear me now?
Yeah, you're back. If you could just repeat.
Okay, great. Okay. Okay. One thing I could try is to dial in, like say, so that I don't know if that will help, because at least that the voice is stable.
It's fine, you're stable. It happens very rarely. So just repeat the last sentence where you have been and it will be fine, I think.
Yeah. Apologize for that. Like my internet was so unstable recently. It's annoying. Okay, it doesn't work anyway. Shoot. Okay, never mind. I'll continue then. So just to repeat, I was saying that to put the basis set in a separate file, you have to really name the file as basisset.dat, exactly as what I was showing on the slide. So that the Crystal program will basically looking for this specific file name in the current working directory. And if the file, the Crystal program find this exactly like this file under this name, this file, for the label, I put in line 9. So basically the carbon, this label is made up, like user made up. So you can name it whatever you want. This is the label. So I put carbon, and then in the base, I put carbon, this label again under in line 2 under this like pound basis. So basically this is a label for and it will basically read the block underneath this label, and so after this label, so basically that's the basis that it will basically trying to interpret and take in. So okay, and of course, like the basis information has to be like put in the Crystal basis format. And the very last line, oh yeah, over here, 21, it has like 99 space 0. Specific line is telling the program that this block, this block from line 3 to line 20 is finished. So this information about inputting basis set in like separate file can be found in chapter 2, section 2, so 2.2 in the user manual. And there are another way And one is, of course, like just copy and paste. So basically, you copy and paste line 3 to 20, this information, this entire block, and replace this carbon by this information copied, and that will also works. Yeah. And okay, so I would also like to introduce like the crystal basis set. This is the carbon basis set I was showing. It's actually a basis set called Hate. The first information, so since it's blocked, I will go back here. So the first information here on line 3 is telling you, so basically starting with like 6 space 5. 6 is telling you this basis set is for the element with atomic number 6. So we know it's carbon. And 5 is telling you that in this basis set, we have 5 valence shell. So like the first shell is starting at line 4, line 11. The third is like starting at line 15 and 17 and 19. So 5 shells. And so for each shell, there's like here we, for example, have 00621 over here. So I color shaded them. So just for easier to like reference to. So basically the yellow, the first 0, the yellow 0 is telling you what type of basis set to be used. Normally, like for basis set, you can find in the this crystal basis set library. I was also attaching a link to this. Those basis set are all going to be like in the standard crystal basis library, crystal basis set format. So usually you'll see 0 on every like this information line, and the green 0 is telling you the shell type. So here, of course, we start with the most inner shell, like the 1s. This 0 is telling you that this is a shell for s orbital. And if it is 1, for instance, over here, we have at line 11, 01. So this 1 was telling you this is the sp shell. So is the exponent, the Gaussian exponent, and then the second column is the Gaussian coefficient for each, like the coefficients for like each Gaussian primitives. So they in linear combination form a better description of the orbital. So this coefficient is for S, and then the second column, this coefficient is for P. So they are like the sp shell. So crystal. And then for more standard, like or general case, instead of putting 1, people usually put 2. So basically they are having separate exponent for S and P. Okay, and the third entry 6 in cyan is telling you how many like Gaussian primitives are in the specific shell we are looking at. So for here, the box, like the cyan box, we have 1, 2, 3, 4, 5, 6. That's how the 6 are coming from. This is not the atomic number. And the 2, the pink 2, is telling you the number of electrons in this specific shell, the electron charge. So we know for like 1s, we are having 2 electrons. So then it is 2. And 1 is just this red 1 at the very end of this line is just a scale factor. And so, okay, so we go through that. Okay, so before we move further, I want to mention another related feature that is using a effective core pseudopotential and showing a example of business vanadate compound on the slide. Number 83 for sure. So but to use a pseudopotential for business, you have to add a number 200 to the atomic number. So here, again, I was basically inputting the space group and the 221 and 3.935 for the lattice constant. Then I was telling them I have 5 atoms in the unit cell. The first one, which it's supposed to be business, so it's supposed to be 83. I put 283. So the program will know that I use the potential for business. So also in the basis section over here, I was inputting at line 17, 83 instead of 83. So so that the program will know that basically this basis that start with a section I boxed in green, basically that contains the pseudopotential information. Yeah, and one important thing is so this 23 at line 19, the manual was rephrasing it to basically to define this number in a way that originally, initially, makes me misinterpreted it, so that I thought it was the number of electrons that was like in the pseudopotential, but it's actually not. So this 23, even though it is actually the information line for the pseudopotential, is telling you that you have 23 electrons in the valence shell. So this is sometimes misleading. So in the valence shell, so I boxed in orange. Okay, so that's just something you have to pay attention to. And the ECP information. So this, yeah. So this 10 in line 17, this 10 is telling you that you have 10 valence. And then this, like the specific information for ECP, like can be found in chapter 3 of the user manual. And if you are using Crystal 17 manual, it should be on page 75. Yeah. So back to the diamond use case again. So in the red box, this entire section, I was specifying the method to be used for the calculation. I use DFT here with selected exchange and correlation potential. A series of the keyword choices can be found in chapter 3.3 and chapter 4 of the user manual. So you will see a complete list of for exchange and correlation potentials and like hybrid functionals and yeah. So everything can be found in the manual. Okay, so in the blue box, we are inputting the computational parameters for convergence and accuracy control. This will include, like, for example, the tolerance for the total energy, like the 2 electron integrals, like tolerance, and for instance, the mixing percentage of Fock matrix, and the smear level, like basically adding smearing for metals. And a list of options can be found in page 29 and page 79 in chapter 3.3 of the user manual. So basically a list of keywords with like detailed explanation for what each keyword is used for. So that would be the general input file for crystal calculation. And one additional thing I just wanted to mention is the supercell feature and atom spin. So showing here is a calculation for anti-ferromagnetic bismuth vanadate. And for A-type AFM, we are basically, for this specific compound, we are basically and we compute this supercell using the supercell keywords. The 3x3 matrix I was showing here are basically actually converting the old translational vector to the new translation vector, like the old translation vector of the original unit cell to like the supercell translation vector. And a detailed description of this, how to basically construct this matrix, can be found on page 67 in the manual. And for antiferromagnetism, we also want to specify the atomic spin, and that's here in the green box. Basically, in my case, I want to assign the first vanadium marked in 1 in line 145. The first one is like a label for the first vanadium. I wanted to have like alpha spin. So alpha spin has like 1 as the value. So the first vanadium has 1. The second vanadium, I mark it with 2, has -1, which is the beta spin. So, and the detailed information for setting atom spin can be found on page 83 of the user manual. Yeah, and so the other useful information, I think, now we basically get to how to set up a band structure calculation at the very end of this tutorial, this very brief tutorial. So to basically calculation, obvious informations like the high symmetry path and the coordinates for the high symmetry point of the specific crystal structure.
Yanbing, we don't hear you again.
Then we've lost.
Oh, okay. That's. Oh, can you hear me now?
Yeah. Just repeat that slide.
Okay. Where did I stop?
Just a minute ago.
You said we came to.
I'm just saying, like, in order. Okay. So I was just saying, like, the information provided in this literature, actually the appendix of this literature I found to be extremely useful for getting like the high symmetry and the coordinates for the high symmetry point in the Berlin zone. So I am attaching a link here. So basically you can search for this literature, preferably download this PDF, and then in the appendix section, you'll find information like this on the right. So, okay. So in this case, I am showing, for instance, a diamond result, because so we seen like before that diamond has or actually I didn't show you, but just telling you, diamond has a Pearson symbol of CF8. Okay, I have a slide over here to show you. So basically, diamonds for diamond we have actually, you know what? I was actually showing the nickel oxide, but it's the same. They all are having like CF8, so it doesn't matter. They're all like face center qubit. So yes. So for instance, if I was looking at a nickel oxide example, then the Pearson symbol is CF8. So then back to this information page, we will basically specifically in the appendix of this literature looking for this specific Pearson symbol, so CF. So I know this corresponding to a face center qubit. So under this section, it provides us the primitive lattice, and then this information, I think you can also like find on this page as well, which is corresponding to here, like the primitive, they name it primitive vectors. So A1, A2, A3, and they have it in this vector format. And in this page, they have it in this matrix format, but it's the identical thing. So in this table, it's providing you the coordinates for the high symmetry K points that are specifically specific for this specific, like the face center cubic. So even for instance, same. So for example, for another like hexagonal structure, you might also have an endpoint, for example, in their like Berlin zone. The coordinate is different. So make sure to look at. Also, they are providing you a plot of like this like the Berlin zone, and also a path here. We know for FCC, we have a path that is from gamma to X, X to W, W to K, and so on. So, and I'm just here using an example to show you how to use the information we mentioned before to construct a input file for a basis band structure calculation. So I'm showing here a example band structure of boron nitride file. So I do have to apologize for like using different like example. This is just because I was able to find this example file. I was searching from my previous calculations, and I think that this is like informative, so I use it. So we found the Pearson symbol and for this compound, the boron nitride, using the resources I basically introduced before, and then I basically searched in the appendix of the literature I mentioned for HP. So because Pearson symbol for boron nitride is HP4, so I searched for HP. And in this way, create point and this is information I would definitely need for this input file for the property calculation. Before submitting this property calculation, of course, we need to submit a regular crystal calculation. So with the crystal executable, so now you might notice the path I pasted here is actually having named crystal property to submit a crystal calculation for like a regular crystal calculation like we showed before. And then you have to basically use this property executable along with this input file. And this so whatever you want to name it, but it has to have the extension D3. Okay, and the keyword NEWK tells the program to conduct eigenvector calculation. And the second line basically is the shrinking factor for the reciprocal space. So we are running A by A by A calculation, so I put A. And the line 3, the one in line 3 is telling the program to compute the Fermi energy. We definitely want to have the program to compute this so that we can have the plot with like all the bands correctly shifted. So, and if we just stop right at line 3 and add a keyword for printing reciprocal lattice information, this program will basically generate original k-point set. So the original like A by A by A k-point set. But to plot the band structure, we definitely need the eigenvalue of k-points along the high symmetry path instead of the original k-grid. So instead, keyword in line 4. And after this keyword, this line 5, so right after this band keyword, this line can be anything. So it's just a string line. So you can input anything that basically are providing you the information, what's going on in the input file. So I put BN, the boron nitride in this case, just for my own reference. So line 7 to line 13, which I boxed in green, is basically specifying the scaled coordinates of the high symmetry path. So like I boxed in orange, we are looking at the path from gamma to M to K, K to gamma, and so on. So I did not include the two segments L to M, K to H here. But if you're interested, you can always append these two segments below line 13. So you basically have to put them in order, just as the order here in the path. And so like in line 7, we have like the gamma point to M point, which is the first segment, gamma to M. So here I put 0, 0, 0 because 0, 0, 0 is the coordinates for gamma point. And one thing you might notice already is like I put 6, 0, 0 for M coordinates. So in the table, we find that M has 1 instead of 6, 0, 0. I put, this is because crystal are taking integers for the coordinates. So it does not accept like 0.5 or 1/2 as input. So I have to basically scale everything in this table, those fractional numbers, to be an integer. So what I decided to do is to add a scale factor 12. So 12. So 1/2 times 12 is 6. So I put 6 here. And for example, I have like k point. K point is 1/3, 1/3, 0. So times 12, I have 440 in the input file. So the crystal does not accept fractional or like floating numbers. Yeah. And so basically, we have 1, 2, 3, 4, 5, 6, 7, 7 lines, like line segments. This is because we have like 8 total k points, so like 7 set intervals. So we have 7 lines here, and that's basically the first entry of line 6. So it's telling you we have 7 lines over here. And this 12, again, is the scaling factor, the shrinking factor defined in the manual. So basically, I use 12. So the program will know to basically divide this 12, all those indices like inputting here by 12. And 115 in line 6 is telling you, it's basically you decide. I put 115 because I want a total of 150 k points in total. It's approximately like 20-ish k points between each like line segment, like more or less. So this is like I'd say that number definitely can be reduced like to 50 or something if you just want to get a like very like preliminary plots for like quality assessment, for example. So you don't have to add too many points. And if you want to generate like a very fine diagram, like plot, you probably want to increase this number. So, and the fourth and fifth entry, like 1 and 20 here, are the first and the last band, the index of the band, to be included in the plot. So for boron nitride, I don't use any superpotential, so I put 1 and 20. So starting from the most inner band to like some band in the valence, and some unoccupied band, I mean. So the sixth entry over here, this again 1, is telling the program to format the output file so that it can be used for plotting. Okay, so that will be okay. And to run this input file again, so we need, like I mentioned before, a new executable called property instead of crystal. So you really have to pay attention here. And again, I'm not sure if this path is still working. It's just like the path I used by the last time I ran the crystal calculation. And just to mention one more thing, a full list of keywords for conducting property calculations can be found on page 259 of the manual. So basically, you can conducting calculations for density states, electrostatic potential maps, for like charge density maps, and molecule population analysis, and etc. So and the input file itself has to be named with like a D. And you probably want to also name the output file differently from the previous crystal calculation, so it doesn't overwrite your output file. So, and what else? Okay, so if, say, you submit the calculation, this line, to the, and then it runs successfully, basically you will obtain, apart from this output file, this I name it bn.band.out, another file called band.dat. This is a file generated by Crystal that contains all the information you needed to plot, to generate a band structure plot. So if you open this file, So what I'm showing here on the top of the file, boxed in red, is so basically this file was actually a calculation from a whatever compound with 4 high symmetry points in the Brillouin zone. I only use 4 high symmetry points. I want to use this example because it's like simpler. We only have 4 points so to look at. So for this 4 selected high symmetry point, this crystal program is telling you like the specific location of this point. So for example, the first high symmetry point, which I assume is probably gamma or something, is the first K point along the path. And the second high symmetry point is the 56th point along the path. And the third point is the 119 point along the path. And like the last high symmetry point is of course the 115, because in total I use 115 total K points. So, and the other important information is listed here. So in this blue box, so like I said before, we have like 4 high symmetry points for this calculation. And for plotting purposes, we want to convert the 3-dimensional K point path. So because each K point has a XYZ coordinate, this 3-dimensional K point coordinates into 1 dimension. And basically, so in this way, they can be like plotted, say along the x-axis in 1-dimensional, right? So the K point path. So, and this is done in general, like by dimensional coordinates between like each consecutive K points, and then the elemental wise, we square the differences elemental wise, and then we sum the XYZ coordinates into 1 number for each point. So now basically you have a 1-dimensional array, and then you take the elemental wise square root for that for the elements in the array, the 1-dimensional array, and then take cumulative sum along the K point path. So basically now you have like a 1-dimensional path from 0 to certain number absolute value, so that basically you can use that for plotting. And basically Crystal, of course, already done that for you. And so the method I was describing was just a general way of doing that. I'm not 100% sure what exactly was done inside the Crystal source code, but Crystal do that for you. So now you it's whatever I was boxed in blue was giving you the core path. So the first point is of course at 0, 0, 0, and the second point, high symmetry point, is at this specific value. And so basically this is the value that you are going to be like using for plotting. And last thing, so after this header block of that file I was showing in the previous slide here, you will see the rest of the file contains the information for the, of course, the eigenvalue of for plotting the band. So, so for every single line over here, the first entry is actually the 1-dimensional coordinates for the K point. So basically, every single line corresponding to the eigenvalues for that specific K point. So in principle, we have 150 lines in this file for like this. So the first entry is, and from second entry till the end of the row, it's actually the band of that specific K point from small to like high. And so basically that's all the information you need for generating the plot. And with all the information, you can just write a short Python script for generating a plot. And I'd also want to mention that there's an easy way of generating a plot just for like preliminary quick quality check. And I'm attaching the link on the slide, and the website looks like this. This is provided by Crystal. So if you click on make a plot, it will take you to, it will actually show you a the drop-down menu, and you will see a bunch of different options over here, including like making density of state plot, vibrational spectra, etc., etc. And of course, you will need the corresponding output file by like for each of this like plotting features. This done by like inputting different keywords in the .d3, like the property input file. So we will be clicking on the band structure plot link over here. So this will take us to this page, and you will be able to upload this band.dat. So this file, the band.dat file over here. And once you upload it, so I'm showing a page for a silicon calculation. So I uploaded a that band.dat file I got from a silicon band structure calculation. So it is pretty much this plot at this point is like zoomed out. So because it's trying to include all the bands that are available. So including this like box in red, the very low lying core band, like the energy corresponding to it was like below like -60 Hartree. So we definitely are not quite interested in that. So what is like selecting the area I boxed in green, and it will automatically zoom out. So here's what it looks like after the zoom out. So zoom in. You can move your mouse along this K-point path, and the actual eigenvalues will basically be displayed. And this is, of course, a semiconductor, a silicon. So this is how to use this like band structure plotting features on the Crystal website. And I was also trying to show here, this is what I found personally to be useful, especially for beginners, a list of like crystal geometry input examples. And the list is definitely longer than what I have here. So this is just a screenshot, but there's like more down below on the page. So here's the link. So for the like beginners, better like you probably want to also check this out to get a like taste of how different types of calculations in crystals can be like the input file can be constructed. And yeah, I think that will be the end of this tutorial. And I'm sure there's like that I'll stop here.